Welcome to the third screencast for Chapter 7, continuing our study of covalent bonds and molecular structure. We've already seen several examples of Lewis dot structures for molecules and for ions, and one question is, are there exceptions to this method? And if we look at the molecule BH3 and do its Lewis dot structure, we put boron in the middle, 3 hydrogens surrounding it. We note that boron has 3 valence electrons, hydrogen has 1 valence electron, but there's 3 hydrogens, so that's 3 more total valence electrons from hydrogen added to the 3 from boron, which is 6 total valence electrons overall. We put the valence electrons in between boron and the hydrogen atoms in pairs as bonds, and we note they're all used up at this point, short of an octet for boron. And that's what happens. Boron doesn't have enough electrons around it to support 4 bonds typically, so boron often forms what are called electron deficient compounds. In this case, BH3 is electron deficient. We have less than an octet around the boron, and this happens when we have an element like boron that is before carbon in the periodic table. Now, how about something like PCl5? Well, PCl5 is going to have a phosphorus in the middle and 5 chlorines around it. Phosphorus has 5 valence electrons, chlorine has 7, but there's 5 chlorines, so 7 times 5 is 35, plus 5 more is 40 total valence electrons. And if we start putting the 40 total valence electrons around this atom in the middle and make bonds to the atoms on the side, we'll have a pair of atoms, sorry, a pair of electrons between phosphorus and each of the chlorines. And that's 2, 4, 6, 8, 10 electrons so far. And now we'll have 12, 14, 16, 18, 20, 22. We're trying to get 24, 26, 28. We're trying to get octets around each of the chlorines. 30, 32, 34, 36, 38, 40. And we have our valence electrons all used up. And what we note is that this gives us 10 electrons around the phosphorus. This is a case of what's called an expanded octet. It's a bit of a silly term because an octet means 8, and expanded octet, which is more than 8, well, it's no longer 8. So that's a bit of a weird way to state things, but it's what chemists use. And here we have an expanded octet, more than an octet around the phosphorus, and this can happen when the central atom, in this case the phosphorus, is in the 3rd row or beyond in the periodic table. And the reason is that 8 electrons around an atom corresponds to the s and p orbitals getting filled, and that totals up to 8 electrons. But if we're in the 3rd row, then there are available d orbitals as well, and those can partially fill, or maybe even more than that. And so we can go beyond 8 electrons to 10 or 12 or even more around the central atom. In this case, it's 10. And then just note, of course, that we could write our substance here as bonds between phosphorus and each of the chlorines, and then fill in our valence electrons around the chlorines, and this is often the preferred way to draw it because we show lines to represent the bonds rather than pairs of electrons. So we still have 40 electrons, but now we have 5 bonds, which corresponds to 10 electrons around that central atom. Okay. We could do some more examples, and I'm going to suggest that maybe you try doing CS2, SF4, and CO3 minus 2. And those could be good examples to try, and then we'll come back and on a future screencast post the answer to this, how you draw the Lewis dot structure for each of these 3 molecules. Okay, a little bit of summary. Note that when we do Lewis dot structures, we can have electrons that are involved in bonding, so a pair of electrons that makes a covalent bond, or we can have lone pairs of electrons. We can have multiple bond formation, like double bonds or triple bonds. We have exceptions to the octet rule. You should certainly be sure to be aware of hydrogen, which only gets 2 electrons around it. But then also there are electron deficient species like boron and beryllium that are before carbon in the periodic table. And there are expanded octets that can happen when the central atom's in the 3rd row and beyond. Also, we've been just making a certain element or atom the central atom without a lot of explanation. And the central atom, there's several ways to predict which atom is going to be in the middle. It's often the one that's written first in the formula, so CS2 or SF4, the first thing written, the carbon in CS2 or the sulfur in SF4, those go in the middle. Whatever gives the most symmetric molecule, often that's the atom that goes in the middle. And then we'll talk about this in more detail in a little bit, but the atom that wants electrons the least is generally the one in the center of the molecule. A couple other things to be aware of. There are some nice bonding shortcuts in covalent bonding if we are use the periodic table, and note that elements in group 3A or 13 have 3 valence electrons. Each of those valence electrons can share with another electron from another atom and form a bond, so they typically form 3 bonds. Atoms in group 14 or 4A, that's the carbon series, have 4 valence electrons and tend to form 4 bonds. And then elements in the 5A or 15 group have 5 valence electrons, so 2 of them are already paired, and there's only 3 valence electrons that are unpaired, so it tends to make 3 bonds. And then similar reasoning, oxygen, the elements in its column or group 16 or 6A have 6 valence electrons, only 2 of which are available for sharing electrons and bonding. And the halogens, group 17 or 7A, have 7 valence electrons, only 1 of which is available for bonding. And then, of course, the noble gases, they're pretty happy the way they are, and they tend not to form any bonds at all. So this can be a useful way to think of things in terms of number of bonds formed by an atom in groups 13, 14, 15, 16, 17, and 18, or 3A, 4A, 5A, 6A, 7A, and 8A.